Welcome to solverfy.
Okay, so for this one, we're given that we have a wire and it's in a loop and magnetic field is changing within the loop. And the goal is to get the power dissipated through the loop due to the induced current. And so, first of all, I want to take a step back and think a bit about the properties of this wire. So they're given that it has a length of 50 centimeters. Okay, wait, sorry about this. I'm having technical difficulties. Okay, no more. So the length is 50 centimeters, so that's a half meter. And the diameter is 1 millimeter. So the radius is 0.5 times 10 to the minus 3 meters. And we need to get its resistance in order to determine the current properties, which would determine the power dissipation properties. And so we have to use an old formula, which is rho is resistivity times the length divided by the cross-sectional area. And the resistivity of copper, I looked it up, and the number I got was, where do I have it written down? 1.72 times 10 to the minus 8. I'm just going to not use the unit. Let's see. I guess it would be ohms meter. Okay, that wasn't that hard. So we have the length, and then we can get this cross-sectional area is just this pi r squared. I'll just write that like that, pi r squared. And then okay, sorry. So that's the radius of it struck me to make sure I differentiate between the radius of the loop and then the radius of the cross-sectional area. So I guess R is going to be the cross-sectional area. Anyway, so when I put this into a calculator, I got 0.0109 ohms. Yeah, okay, so now we kind of have some of the background problem done. Let's go from there. So we want to use Faraday's law. E is minus the flux, derivative of the flux with respect to time. Flux is BA, and the magnetic field is constant over the area, so it's just BA. So then A isn't time dependent. We can stick it on the outside, and so then we just have A dB dt. And then we're going to eventually need the current. Well, I'll just leave it as EMF, actually. Okay, so A is going to be this pi times the radius of the loop, which I'll call big R. So just to label it, big R is rad of the loop. And the d by dt we're given. So I'll go ahead and put it in this little givens box, that dB dt is 10 times 10 to the minus 3 Teslas per second. And yeah, so with that, plugging in all these values, oh yeah, we need to find R. So we know that, oh wow, I just realized there's already an R for resistance. All right, well, when in doubt, let's put a subscript. RL means R of the loop. Oh, I actually did put the L here. That was so serendipitous. So yeah, so another little side calculation. This time I'll do like the side calculation here. So we know the circumference of the loop is, oh, well, we know the circumference is the 50 centimeters, right? So circumference is 2 pi r of the loop. And so r the loop, and then the circumference is the length. So I'll put that length as that. Therefore, RL is 0.5 meters divided by 2 pi. And when I plug that into a calculator, I got 0.0796 meters. Great. For RL. So now we have all of that, and we can get that the EMF is 0.000199 volts. And then to get the power dissipated, we want to use P is V squared over R. We don't want to have to find current, although I guess it's fairly simple. We've done most of the work already. And I'm sorry, I'm using voltage and EMF interchangeably. Hopefully you're used to that by now. So I'll just do this. It's E squared divided by R. So that R that we found here goes here. The EMF goes here. And then when I plug that into a calculator, I got that 3.63 times 10 to the minus 6 watts are dissipated.